Hey everyone, and welcome to today's Explainer. Today, we're zeroing in on a super crucial, though sometimes overlooked, metrological process. We're talking about the discrimination test for digital weighing scales. Let's jump right in and see exactly how we guarantee absolute accuracy.
Okay, let's dive into this. Here's our game plan for today. First, we'll cover what the discrimination test actually is. Then, we'll look at a specific 60-kilogram scale example. After that, we'll go over the prep and the rules, followed by a step-by-step walkthrough of the digital test itself. And finally, we'll figure out how to determine the actual results.
So Section 1. What exactly is a discrimination test? We really need to understand the why before we get into the how.
Basically, in the world of metrology, discrimination is an instrument's ability to react to tiny, almost microscopic variations in weight. Think about it. If a scale is sitting perfectly balanced and we add or take away just a hair of weight, that digital display absolutely has to register the change. Doing this test proves the scale is perfectly sensitive, which is what guarantees total fairness when we're measuring things out in the real world.
All right, moving on to Section 2. Let's ground this theory in reality by setting up our specific case study, a real-world 60-kilogram scale.
Now, what's really interesting about this slide is that we're focusing on a Class 3, digital, non-automatic weighing instrument. It's exactly the kind of scale you see every single day at the grocery store or in commercial shops. But testing these digital bad boys, it requires a highly specific, very technical workflow compared to the old-school mechanical ones.
Let's break down the foundational parameters for our specific scale so we know exactly what we're working with. Our maximum capacity is 60 kilograms, and it's an accuracy Class 3. Now, here's the really important part. Both our verification scale interval, which we call E, and our actual scale interval, D, are exactly 10 grams. So the scale steps up in 10-gram increments. Keep that 10-gram figure locked in your head because literally all our math relies on it.
Okay, Section 3, the preparation and the rules. Let's do a little essential math before we actually start the test.
Before we even touch the test weights, we've got a rule to follow. We need fractional weights that are equal to exactly 1/10 of our E value so we can find the scale's precise changeover point. Since our E is 10 grams, 1/10 of that perfectly calculates out to 1 gram. Basically, we're going to need a handful of tiny 1-gram weights to push this scale sensitivity right to the absolute edge.
Now pay close attention, because this is the most critical number in the whole procedure, 1.4 E. The rules strictly dictate that our extra testing load has to be exactly 1.4 times E. Do the math, 10 multiplied by 1.4, and we get exactly 14 grams. That 14-gram weight right there, that's the star of the show. That's what we'll use to prove if the scale is truly sensitive. And just so you know, this rigorous test isn't just a one-and-done deal. To be fully compliant with legal standards, you actually have to perform this exact same procedure at 3 different stages: at the minimum load, at a half load of 30 kilograms, and finally at the full maximum load of 60 kilograms.
Ready for Section 4? Let's move to and see how this builds as we slow down and do a step-by-step walkthrough of the digital test.
Let's imagine we're in the lab right now doing the half-load test. First, watch as we place a certified 30-kilogram weight right on the platform. The scale stabilizes at 30.000 kilograms. Now, we carefully add our 10 tiny 1-gram weights, stacking them one by one on top of the load. We do this to push that digital indication right to the brink, forcing it toward a lower number.
Now for the delicate part. Watch closely as we start taking off those 1-gram weights. We don't just grab a handful, we remove them one by one. We're keeping our eyes locked on that digital display. We are waiting for the exact moment the indication unmistakably drops by a single 10-gram interval, say going from 30.010 down to 30.000. The absolute second it drops, we stop immediately. Bam! We found our changeover point. We've perfectly isolated that exact breaking point where the scale is balancing between 2 digits. So what do you think is the critical next step here?
Well, here is the exact sequence. First, you replace one single 1-gram weight back onto the platform. This brings the scale back to its initial indication, restoring perfect equilibrium. Then, with a super steady hand, you gently place that crucial 14-gram test load onto the receptor. No shock, no dropping, just smooth and steady.
And that brings us to Section 5, determining the result. Did our 60-kilogram scale pass or fail? Let's find out. So the crucial point is this simple final comparison. The display absolutely has to react.
If our initial indication was 30.010 kilograms and adding that 14-gram load makes the display jump up by exactly one scale interval to 30.020, then the scale passes with flying colors. But if the number doesn't increase by exactly 1D, the scale just isn't sensitive enough, and unfortunately, it fails.
It's honestly incredible how a tiny 14-gram weight can completely verify the pinpoint accuracy of a massive 60-kilogram machine. At the end of the day, metrology is all about standardizing trust. So, how will you apply this strict 1.4E standard to ensure pinpoint accuracy in your next inspection? Keep questioning things, keep verifying, and thanks so much for joining me for this explainer.